Hello again, my dear friends, and welcome back to the Informatics 2 class. And this time we're going to start lesson 21, which talks about a new topic called recursion. In this presentation, we're going to introduce the concept of recursion. So we're going to start with a basic introduction about this whole topic, and then define what we mean by recursion. And after that, we're going to introduce the concept of recursion tree and see what that means and how it works. And then we're going to talk about the relation between subprograms and stack, the computer stack. Okay, and this is actually a very typical application to where we use stacks, as a matter of fact. And then we're going to talk in depth about the recursion process. After that, we're going to give some application examples on the use of the recursion concept. Okay, let's start. Well, in many times when we write our programs, our program will have one main module, and then that module could call other subroutines or subfunctions within my program. So for example, my application will have, let's say, 3 subprograms in it, and they're named A, B, and C. Then let's assume the following scenario, that when you start executing your program, you're going to definitely start from main, as usual. Then let's say in the middle of your program, you need to do something, and that particular task is performed in a function called A. So in the middle of your main program, in here, you're going to make a call to function A. What's going to happen? Well, you're going to stop the execution in the main program right there, okay? Stop the task temporarily, and then you're going to jump to this module, which is called A. All right? Now, before you go actually into the module A and start executing the statements in there, you have to put a kind of tag, a label, to where you have reached in the main program, so that when you come back, you know where to continue and where to resume the execution after that. Okay, so this thing has to be done somehow. Okay, and now, then after I save what we call this return address, then I can go safely now to module A. And let's say in the middle of module A, I decided to call this function B. So again, I need to save the status, the return address, and then make a jump to this module B. Module B starts executing, and in the middle of this, we're going to make a call to function C. And this is a typo here, not B, but rather C. Okay, so again, I'm going to stop the execution in this module, all right, and make a jump to this module, which is called C, and then start executing. All right, and of course, this could call other functions and so forth. Let's assume that this statement is not there, basically, and that these statements are going to just execute right away. So what we have, we started this, but we did not finish it because we had to make a jump to this module. And we started on this one now. This one is waiting, okay? But in the middle of the process, I had to make a call to this function here. So again, I have to stop the execution on this module. And then I will start the execution here. Well, I found that in the middle of this process that I need to make a call to this function. So again, I'm going to stop the execution in here and go there. So basically, when I'm executing these statements, none of these functions have finished the task. This one is waiting for A to finish. This one is waiting for B to finish. And this one is waiting for C to finish. Okay? So basically, then what's going to happen? Main is not going to finish, waiting for A to finish the task it's performing. Well, A is waiting by itself for B to finish. So again, A is kind of temporarily paused because it's waiting for results to come back from module B. And by the same analogy, B is waiting for C to finish before it can go. And that means all of these modules are actually in a sort of wait state, paused, waiting for the result of this module. So as soon as this module finishes the execution, it's gonna return back to the next line right after this call statement in module B, and then it's gonna continue, resume the execution till it reaches the end. Once B finishes, it's gonna return back, all right, to the line right after this one into module A and continue the execution till it finishes. And then once A finishes the execution, it's gonna return back to the main program and continue the execution till I get to the very last statement in the main function. So it's kind of a sequence through which the different subprograms, the different functions go through, one waiting for the other. The calling is waiting for the called function to finish its task and return back to it. Each time I make a call to any of these functions, I had to save in some place the address of the next statement that comes after the call statement. Okay, and this is what we call the return address. Without this address, I can never go back to the calling function and resume the execution, because the gears has been changed to the other function, and there's no means for the CPU, for the microprocessor, to know what was exactly the last statement it has executed in the calling function. Okay, so we have to save the return address, at least that return address. Of course, there is some other data that I need to save, and we're going to see what exactly we're going to be saving as we move on in this process. Well, this is very typical actually in real applications. Basically, we're gonna the save place where I'm gonna put the actual return address and whatever other data needed, so that I can return safely to the calling function, is the stack. So the stack basically is a portion of the memory. Here's the memory of the system, computer memory. And there's a portion in this memory dedicated for the stack. And basically, it is just a stack, the same as the concept of stack we talked about earlier. So basically, I'm going to be pushing always to the top of stack information coming from the calling functions with regard to the return address and any other important data that I need to save, okay, in here, and then to make the physical jump to the other program or to the other function. Okay, and once this other function now returns, finishes the task, then I will go back to the stack and pop from the top of stack this return address and other relevant information about the calling function. Based on that information, I will continue and resume the execution of the main program or the calling function. So when a subprogram requests to use another, to make a call to another subprogram, then the stack is used to save the return information about the requesting subprogram. So we either call it requesting or calling subprogram, and this is called, the one we go to is called the called program or called subprogram. This is a scenario which shows me with time how things go when we make calls to other functions. Okay, and this just is just an illustration on the use of stack with time and as we move on calling functions and other functions and so forth. So basically what we see in here is that I'm going to start with main, and then time goes, all right. Now at this moment, main decides to call the function A. So all right, then I need to save on top of the stack whatever information with regard to the return address and other relevant information on top of stack. So this shows what I put on the stack. Okay, and then I jump to A. In the middle of A, I decide to make a call to function B. Well, then, okay, I need to save on top of stack the information about A so that I can return safely to the next statement in this module. All right? So basically in here, I still have on the stack the return address and other relevant information about main, as well as A. I need both of these because actually this did not finish yet. It's still waiting for A. And A is now gonna call B, all right? That's why I need to keep information about it here, and then I'm gonna make the jump to B. Okay, I go to B, and then I realize there that I need to call the function C. So I need to push then the information about B on top of stack, and then I go to C. Well, I'm executing C now. I don't need to go anywhere else, so I'll just finish the execution of subprogram C. Nothing goes to the stack if I don't make any calls, and let's say C finishes. Okay, C finishes, so I'm gonna go back then and resume the execution of B. In that case, I'm gonna pop from top of stack the information about B, all right? And then I can execute it. So I will remove this from the stack, okay? And then I'm gonna keep executing in B till I get to the end. Well, after that, I realized, according to this scenario, that I need to make a call to C, so I push the information about C, and then this function is calling D, and so forth. So that's the way it goes, actually. Each time I have to make a jump from one program or one subprogram to another, then I need to go to the stack, to the computer stack, to save the relevant information about the function, the calling function, and then I make the jump. Okay? Well, at some situations, the function might call itself. Like I need to perform the exact same task again on some other parameters. Well, this is like just another call. Okay? So the main program here, in this part, the main program is going to make a call to function D. So that's okay. You push to the top of stack information about main, and then you call the function D. You start executing with D, and then you realize that you need to call this function again. So you need to save on top of stack the information about D. True? And then you started executing from the beginning on the new status of parameters in this module D. Well, in the middle, you decide to call the function D again. Okay, do I depend on the return information that I already have about D? No, because the information that I have this time are different from what I had the other time. All right, so I have to push to the stack a new frame, all right, containing the return address and other relevant information about D to the stack. So yes, I could have several instances of this module, the same module, in the stack. Well, physically, what I have in here is some different relevant information about the status of this module D from the first time I called it to the second time, to the third time, and so forth. So yes, the function can call itself, and there's nothing wrong with that. And that's basically the idea of recursion. Recursion means when the name, actually it's the name for the case when a subprogram makes a call to itself, when it invokes itself again and again. So basically, if the main program actually, this is main, okay, and in the middle of this main, I make a call to this function called D, according to our example. So I'm gonna save on top of stack information about main, and then I'm gonna make the jump to this D module. Well, I start executing, okay, and in the middle here, for whatever reason, depends upon the application, I decide to make a call to the same module. All right, that means it's another instance of the same module D. So again, I need to push to the top of stack the relevant information about the status here, okay, and then I'm gonna make the jump to D again. So it's like as if I have another copy of the same module, okay, another instance of the same module. And then in the middle here, I might decide to call this function again. All right, so this process of having a function calling itself again and again is what's so-called recursion. So recursion is the case when a subprogram or a function makes a call to itself several times. All right. In regard to stack, recursion is not different from any other program calls. Actually, each time there is a jump to whatever program or subfunction, anytime I have such a case, then I will push to the top of stack the return address and other relevant information about the calling function. Well, now the function is calling another function, or the function is calling itself. As far as the stack goes, there is no difference at all. Each time you want to make that jump, you have, before you jump, to save to top of stack in here the return address and other relevant information. So as far as the stack goes, then it doesn't matter whether the called function is the same as the one you're executing at the moment, or it's some other sub-program. Recursion tree. Well, remember this scenario, the time and stack thing, which we showed a little while ago, like a couple of minutes ago? Well, we could put this in a different graphical way, which shows actually the sequence of events that occur during the execution process of the main program, with all other subprograms that I'm going to call or invoke during the process of the execution. Well, this kind of a graphical view is what we call a recursion tree, or a tree in general. The tree is the sequence of events that shows me how the execution actually is occurring as I start from main to other subprograms, calling each other's, and so forth. So a graphical diagram that shows the order in which subprograms are invoked is called a tree. Well, in the case of recursion, and that's when I have a function calling itself again and again and again, well, because I'm talking about recursion here, all right, then this kind of tree is called recursion tree. So the tree in general, or traversal tree, which we call sometimes, is the graphical view of how events occur when I execute programs and subprograms. Now, for the special case, when I have these subprograms calling themselves again and again, then the tree is called recursion tree. Well, actually, if we look at it, it looks like a tree to where I have root and branches. All right. However, this tree is actually upside down tree, to where I have root on top and the branches go down instead of the actual physical tree that we have in our real life. The top of the tree is what's called root. The tree root corresponds to the main program, and that's where we always start, of course, the execution. So I start from main, that's my root, and then I start branching here and there within my subprograms or within my functions. The tree that shows the recursion is, as I said, is called recursion tree. Okay, so now subprogram call tree. Well, here is a typical tree to this particular function that we have talked about a second ago. According to this, these circles actually correspond to the different functions or subprograms we're calling. Okay, so circles correspond to subprograms. Actually, we refer to the circle by the name node. So we call these nodes in our tree. All right? And then this orange path in here shows the sequence of events actually and the way we traverse the tree from the beginning. So I start from main calls A is calling B, and then it returns, calls C, D, and then I return to C, finish, go back to A, go back to main. Main is calling D, D again, returns, and we're back and we're done. So basically, it shows the traversal, the sequence of events that occur throughout the execution phase of the whole program. The recursion tree, however, is basically this part here, which basically talks about a function calling itself again and again. So this portion of our tree in this example is actually a recursion tree. So recursive calls appear as different nodes that have same subprogram. Actually, different nodes, that's the way we draw them, as if they're separate functions, okay? So I repeat these nodes again and again as far as I go with these call statements. During the traversal of any tree, nodes are added to or deleted from the path back to the root. So I add a node whenever there is a new call for a new function, or I delete that node whenever I return. This is exactly similar to insertion and deletions from stack. So each time I make a call, then I'm going to add or push something to the stack. And each time I return from any of these functions, I'm going to pop something from the stack. So that's like insert and delete from stack. And we know these operations very well. Stack frame and system stack. Well, talking about this stack, we're going to define two basic things. The system stack is actually this block of memory reserved in here actually for pushing and popping information about called functions. So when one function calls another function in C, all parameters that I pass, as well as the return value and the return address, are actually all together pushed to the top of stack. All right? So it is actually transferred via the system stack. So I push them to the top of stack, and then at each cell, this whole package that we pushed is called stack frame. So the stack frame is that package, all right, that record about the calling function that we push to the stack, we put on top of the stack whenever I make a call to another function. The stack frame then contains the parameters of the call, whatever parameters I pass in the function, local variables of the calling function, next statement in the calling function, and this represents actually the return address. So as I said, it is the return address as well as other relevant information. This relevant information is actually the parameters that I pass and the local variables. And of course, a place for a return value if there, and this is part actually of the parameters that I pass sometimes, or if the function returns a value, then that place is going to be saved as well. The process of calling a function. The calling function, okay, which is main or any function from which I'm going to call another function. Whenever I reach that call statement, then it's going to push to the top of stack a stack frame for short. The called function, on the other hand, all right, it's going to go to the stack to get the parameters because it's going to work and operate on these parameters. And so that it goes right away to the stack to retrieve these parameters and work on them. Perform calculations on these parameters and then return. The call function places the return value on the stack as well once it finishes the execution. It transfers control to the next statement, and that's when it returns actually. So I pop from the top of stack this return address. The calling function restores local variables once I return now to the local function. It returns the local variables from the stack. It uses the return information or the return value from the stack, whatever value calculated as a return value for the function. It's going to be returned. And then after that, if a function calls itself, then recursively several times, then separate copies or separate stack frames are going to be pushed on top of the stack. Each time I push a new stack frame containing whatever new parameters I'm passing and whatever. Yes, the return address could be sort of the same because I'm going to return to the same next statement. However, the parameters and other arguments that I'm passing are going to be different. And that's why I have to send to the stack a new frame each time I make a call to the function. Okay? Hence, the amount of stack required to implement a recursive function actually depends upon how many nested calls I'm going to make. So it depends what we call on the depth of the recursion tree. Okay? And of course, not on the number of times I'm calling the function. Because what is the difference in that? Well, the difference is when main makes a call to this function D. Okay? Well, I could make a call to D and then go back. So before I go, I pushed to the stack a frame in here. Okay? And then processed whatever I want to process in here. And then I return. Once I return, this is going to be popped from the stack. You call it again one more time. And then a new frame is going to be pushed. But in this scenario, I only have one frame in the stack each time. All right? So it doesn't matter how many times you make a call to this function, but rather how many times, nested times actually, recursively, you call that function. So in this scenario, if I call and return, I'm going to have just one entry on top of stack. But if I have the following scenario, main, call to D, and then D is calling D again, and calling D again, and so forth, and then I will have a stack of frames on top of each other's, okay, with different parameters, of course, and return addresses. Okay? In this case, I'm going to have too many nodes in my recursion tree. So it depends upon the depth of the recursion tree rather than the number of times the recursion function has been invoked. The recursion process. Well, it's very important to understand this process. And this process consists of mainly 2 or 3 very basic steps. Every recursion process consists of a smallest, what we call base or terminating condition that is processed without recursion. The very basic operation that I perform, all right, and I don't need to call any other function to do that. Okay? It's a basic step. All right. The second, well, a general case or a general method that reduces a particular case each time I make a call to that function. So that means when I reduce the size of the problem, then with these consecutive calls again and again, this case is going to keep reducing down and down till I reach to the situation where I have the base case, the one I talked about in step number 1, and then that one is going to be executed without any recursion. So the base case is called actually a terminating condition, and that means that the function is going to keep calling itself again and again. Each time I make a call, the size of the problem shrinks a little bit. All right? And then it's going to call itself again. Shrinks. As far as the size of this is still sort of big, then I'm going to keep calling the function itself again and again. Once the size of this task is very tiny, base case, then I'm not going to call the function any further, and I'm going to just execute basic statement or statements, and that's going to be my terminating condition, and I'm going to return. All right? So these are the 2 major steps actually in the process. To illustrate this, as a matter of fact, we're going to start with this very simple and typical example, which is to calculate the factorial. You know in mathematics what factorial means? Well, it works on integers actually, and the factorial, let's say, of n, and this is the notation used in mathematics, equals to n times n minus 1 times n minus 2 times all the way down to 1. So for example, the factorial of 3 is basically 3 times 2 times 1, and that is 6. All right? Well, here's the problem that we have, and we want to think about implementing this case using the concept of recursion. all right, to see if that really helps us in writing our code to making it more efficient or run faster. Well, there is a fact in here, which is the factorial of 3 is basically 3 times the factorial of 2, isn't it? Because factorial of 2 is basically 2 times 1, right? So generally speaking, then the general case is that n factorial equals to n times n minus 1 factorial. This is the general case. And this is what we called the second step in the process we just talked about. So this is the general case. What is the base case to where I don't have to call this function again? It's like in this general case, to calculate the factorial of n, then I need to somehow calculate the factorial of n minus 1. And of course, to calculate the factorial of n minus 1, I need to call the function again to calculate the factorial of n minus 2 and so forth. So there is a sort of repetition in the process in here. However, it's known in mathematics that the factorial of 0 equals to 1. This is a fact. And this fact is actually going to be my base case, or what I called terminating condition. And that means once I get down to 0, okay, then I don't have to call this function again. It doesn't involve any factorials on the right-hand side of the equation. And in that case, then I can just execute this statement and return. And that's what we're going to talk about in here. So in terms of mathematics, factorial of n equals to 1 if n equals to 0. Otherwise, it is this, n times n minus 1, n minus 2, and so forth, down to 1. All right. Well, this can be defined recursively in this way. Basically, factorial of n equals 1, which is the terminating condition or base case for n equals to 0. However, if n is greater than 0, then basically the factorial of n is n times the factorial of the n minus 1. Okay? And again, factorial of n minus 1 equals n minus 1 times factorial of n minus 2. So it's kind of repeating itself in here. Given this fact, then I can definitely perform the operation using this recursion process. So we have first to analyze the problem, and that's basically what we have talked about. So I have to find first the base case or the terminating condition, and that's the case of factorial of 0 equals to 1. And then the general case, which is factorial of n equals n times factorial of n minus 1. This is basically the analysis. Okay, calculation. Recursive definition can be used to calculate the factorial then, because I have general case, which reduces the size of the problem from n to n minus 1, and then to n minus 2, and so forth. And I have a terminating condition, which I don't need any kind of recursion to perform it. So let's say I want to find the factorial of 3, then it's definitely 3 times the factorial of 2. Okay, then I need to calculate this. Well, here it is. Factorial of 2 is 2 times factorial of 1. Excellent. The size of my problem is reducing actually as I go with the execution. Factorial of 1 equals 1 times factorial of 0. Okay, factorial of 0. No more recursion. That's the terminating condition. It's 1, known. Okay, so you can return now backward. So you were calculating the factorial of 1. Okay, factorial of 1 is 1 times this. Well, I have this now. So it's 1 times 1. And I return back. Factorial of 2 equals 2 times this. Well, I have that, and so forth. So it's very simple, very straightforward. And the recursion tree is basically a chain, a very simple chain. I start with n minus 1 down to 0. And here's the code. Well, basically, I need to check if n equals to 0, and that's my terminating condition, basically. All right? So if that is the case, then don't call the function again and just return a value of 1. Otherwise, call the function again. So this function is going to calculate the factorial of n, okay? And the precondition is that this number is not negative, and this is a mathematical restriction because factorials are known for only positive numbers. Okay, it's going to return an integer value, and that's the value of the factorial, and takes the integer n as its input. And I check on my terminating condition. If n equal to 0, then return 1. Else, I return n times the name of the function, but this time I'm passing n minus 1. Okay? However, if I want to implement the same function using the iterative way, then I'm afraid I'm going to have a while loop, all right, or a for statement which is going to go from n down to 1 or to 0, whatever, back and forth, and each time I need to accumulate in my accumulator the value of the product or the factorial. So basically, I'm going to have something like local variables count and product, and I'm going to initialize product to be 1, okay, and then start from 2 because it's 1 times 2 times 3 times 4 up to n. Okay, so this counter is gonna go from 2 up to n, incrementing by 1 each time, and basically product is gonna be product times count, and then I return this. So it's a loop in here. I don't have any kind of loop in the recursion form. It's just an if statement. The loop is inherited here, as a matter of fact, when I make recursive calls to the same function. Okay? So I think you grasp the idea now. Let's take the second example, and we're going to go really quick in the analysis of this. Fibonacci numbers. You know this from math, basically. Fibonacci numbers are defined by recurrence relation. And that means that the nth order Fibonacci number, Fn, equals to Fn minus 1 plus Fn minus 2, okay? So at any moment, the Fibonacci number is the sum of the previous 2. Okay, so that's the kind of recursion. Each time I look at the previous 2 elements. That's the general case. What's the terminating condition? Well, simply the terminating condition as known in mathematics is that Fibonacci of 0 equals to 0, Fibonacci of 1 equals to 1. And then if you want to calculate the Fibonacci of n, okay, then you need to calculate the previous ones. To calculate the previous ones, you have to look at the previous, and so forth. So then, yes, you're going to be calling recursively things, and each time you're shrinking the size of your task, and you're going to stop when you reach these terminating conditions. Very simple, very straightforward. So terminating condition is this. General case is this. All right? Very simple and very straightforward. And here is a tree showing the case of finding the Fibonacci of 5. Fibonacci of 5 is basically Fibonacci of 4 and Fibonacci of 3, right? So to calculate this, you need to calculate these two, and so forth. Very simple. So you go through this whole process one after the other recursively, and you can find then the Fibonacci of 5. Very simple and straightforward. And here's the example. We're saying the same thing again and again. To calculate at every step, to calculate the Fibonacci of the number, you need to look at the previous 2. And then once I'm done, I can go backward, and then I will have the Fibonacci of the number that I want. Okay, let's look at the implementation. Very simple and straightforward. It's going to return an integer value again, which is the Fibonacci number. And it takes n, integer n. All right? So I want to calculate the Fibonacci of this n. Well, again, no loops. All right? I'm going to check for the terminating condition. Is n less than or equal to 0? If it's less than or equal to 0, that means there is an error. Just return 0. All right? However, if n equals to 1, then return 1, and you're done. So that talks about the Fibonacci of 0 here, which equals to 0, and Fibonacci of 1 equals to 1. This is the terminating condition. Now, the recursive case is when you have n greater than 2. Greater than 2. If it's greater than 2, then the Fibonacci of this n is going to be the Fibonacci of n minus 1 plus the Fibonacci of n minus 2. So basically, you're going to return this value, and that means you go again and again through this. All right? In here, however, we're showing the implementation using the normal iterative way. I'll leave this for you to look at. It's just simple, straightforward for you to compare between the two implementations. So it's basically straightforward. It's very long, 2 pages in here. However, it's just like 2-3 statements when I use the concept of recursion. Okay? Guidelines. To decide whether to implement a particular algorithm using recursion or using the normal iterative way of doing things, we need to look at the following points. If the recursion tree has a simple structure, all right, like a chain or something like that, then using the iterative way may be the straightforward and the more easier thing to think about. So don't use recursion in that case. If the tree involves duplicate tasks, you might consider another data structure other than stack that could help you make the process a little bit faster. And that's, if you do that, you might find that you don't need the recursion. And if the tree appears quite pushy, lots of things back and forth with little duplication of tasks, then recursion is definitely the solution. Okay? So that's pretty much what I want to talk about so far. Thank you very much for watching. You can refer to the internet, to the UNINETTUNO website, click on the MidNetU project to see this material and many other exercises. Thank you very much again, and I'll see you next time. Bye-bye.